Okay, is it on?
Looks like it.
Is there a red dot?
Where would the red dot be? Oh, I see it. Okay.
I always have a little bit of dead time, and then just be mindful of you, especially if you hear the. Yeah, we've had nothing but issues lately with the GoPro, and it's turning on and off several times during the class, and so I'm having to reorganize, and yeah, it's extra work, but we're making it work.
I forgot my folder with my homework, so I'll be right back.
Okay, so we're going to try to find a confidence interval around mu. So we're going to collect an X bar and an S from some population, okay? We're going to collect these things. But there's more than one different formula we're going to learn today because there's certain conditions that it depends on. Now, let's suppose, there's two suppositions. Suppose the population is normally distributed and we know the population standard deviation. We don't know the population mean. If we knew the population mean, we wouldn't need a sample, would we? We're collecting a sample to estimate the population mean. Now, it does seem a little bit odd at first, because don't I need the mean to calculate the standard deviation? Isn't that part of the formula? Yeah, I mean, you got stuff in minus mean squared. But there are certain situations where that's not necessarily the case. For example, we know that human heights are normally distributed, and we actually know the human height standard deviation. We know that duration of pregnancies are normally distributed, and we know the standard deviation. We know that SATs are normally distributed, and we know the standard deviation before we collect a sample. IQs are normally distributed, and we know the standard deviation. There are scenarios where we actually know that it's normally distributed, and we know the sigma. What we don't know is within the group we're looking at. See, the group we're looking at might not be the population average. So let's say hypothetically we know the population mean of heights, and we know the population standard deviation of heights, but does that mean that's the Mesa College mean? Or might we be taller than the general population? We might be shorter than the general population. Does that make sense? So we'd still need to collect a sample from our own stuff to figure out what our mean is, okay? So with that said, we go out and collect an X bar. If I know the population is normally distributed and I know sigma, then I'm going to use the population sigma every time, because then I can use the z-table. You can't always use the z-table we're going to find, okay? Can we go ahead and close that? For at least until they're done collecting the garbage. So in this case, the error, okay, so before, remember, we called it the z alpha over 2. It's a confidence interval, so I have both ends. Remember? So if it's a 95% confidence interval, we wanted 2.5% in each tail. So it's going to be this times the square root of sigma over root n. Well, that sounds familiar because that's the standard deviation if I have a sample, right? So we've already done that. This is the error. This is the plus or minus. This is actually really, really, really simple. Why? Because we choose this. We choose this. We're given this. Oh, okay. So keep it real simple. Let's suppose that we want to find the average height of a Mesa College student. Okay? And we know that human heights are normally distributed. So let's suppose that the standard deviation for human height, I'm just going to make it up. I actually did look it up, but it's not really important, is, let's say, 16.37 centimeters, okay? We collect a sample of size, let's say, n equals 257. We actually had time to measure 257 different people because that doesn't cost any money. It just takes us, maybe a minute or less. And let's say the X bar of our group was 141.3 centimeters. Okay? Now, whatever the mean of human heights is, that's the mean of human heights, but that doesn't necessarily apply to us. Does that make sense? That'd be kind of like saying the GPA of all Mesa College students is the following number, therefore that must be the number that applies to this collection of people. No, it doesn't. You're a sample. You do not have to be exactly the same as the population. You could be way above that. You could be way below that. You could be right on. So human heights are normally distributed. We'll say this is the standard deviation. I went out and collected a sample of Mesa College students. We found this. So I'd like to know, what is the true mean of Mesa College student? So we know when there's error, it's a plus or minus. So the confidence interval looks like this. Mu is less than x bar plus the error. It's greater than x bar minus the error. Remember, x bar is what we collected. That's the best guess for what the population actually is. Okay? So it's always, whatever your sample mean is, would always be your best guess. Last day we were doing probabilities. P hat was your best estimation of the actual P. But when we put a confidence interval around it, a plus or minus, then we were really sure. Okay? So you with me on this? Now, I want to construct a confidence interval. So we are going to construct, and the usual will be 95%. For the true population mean. Now again, we're collecting a sample and we're trying to apply that sample to the entire population of Mesa College students, which is tens of thousands of people. So if we collected the sample well, then we believe the true population mean shouldn't be very far from our sample mean. Agreed? Is it possible our sample mean could be right on the nose? Is that possible? Yeah, it's not very likely. That's kind of like saying I flipped the fair coin 1,000 times and I got exactly 500 tails. That's possible, but it's not likely. Being close to 500 tails is more likely. But, you know, I've got this. So the only calculation in the problem is calculating the error. Now, if it's a 95% confidence interval, that means that I'm going to report everything between here and here. I'm going to exclude the tails, remember. So that means that 0.95 is here. So 0.025. 0.025 is in each tail. Remember, a confidence interval, you always have two tails. And so that's why we call it alpha over 2. In this case, alpha always means the tail probability. Alpha is always the total tail probability, which in this case, 5% is 0.05. So I have exactly 0.025 in each tail. So the z number I look up, that magic z number, we call it z 0.025. It's the z that goes with that tail. And from experience, we now know that's 1.96. That's the most common one we use. I do not want you to memorize that. I want you to have that available. That's on the formula sheet. And by the way, we have an exam on Thursday. Please don't forget to bring your formula sheets. Right? Those are yours. Those, you own those. You can write on this, but don't lose those. What happens if you lose it?
You print it off campus?
Yeah, print it off campus. I will actually ask people, or I'll have people ask me during the exam, oh, I don't have one, can you give me one? No, you have them, and you have access to them. You can make 1,000 copies if you want. Yeah, don't lose it, or at least, you know, make yourself an extra one. So when I'm doing this problem, what do I have? I have this, that's 1.96. I have this, that's 16.37. And I have this, that's 257. So I have everything I need. So let's calculate the error. So with your calculators, let's get those out. So it's 1.96 times the square root of, is it 16.37 over the square root of 257. I don't suspect this is going to be very big, simply because our sample is huge. That's a good thing, by the way. Huge samples rock. Okay. So let's all calculate that. Tell me when you get a number.
I have a number.
What do you get?
1.980.
Does anybody else get that? Oops, you know what? I'm sorry. I put Just realized, I have too many square roots here, sorry folks.
Oh,
I'm looking at that going, I got the square, my bad, I'm sorry. I saw the square root, then I got excited, I put a square root. There's not a square root on the whole thing, just a square root around the end. I'm looking at that going, I entered it into my calculator correctly, I'm sorry. That was crazy. Because I even said, this part here should look familiar. What's that part there? What is that part there? That's the standard deviation when I have a sample, right? Standard deviation for an individual is sigma. When it's a sample, it's sigma over root n. If n is 1, then sigma over root 1. We know that. My bad. Let's try that again. Got too excited here. So what do you come up with?
I have 2.001.
So 2.00, that's nice. Can I just say 2?
Yeah.
Now here's a question, and this is an important question. If you're in a chemistry class, you're in a physics class, you're doing a calculation. One of the questions everybody asks is, how many decimals do I need to report? The answer is actually simple. How many do I need to report? Look at the information that is given. I'm going to do a confidence interval around mu, and I'm going to use this value plus or minus. So since this is a 1 decimal place number, what do you think is the most logical number of decimals to report that to? Yeah, probably the same. To report it to less or to report to more, it doesn't match all that well, does it? Now, with probabilities, we go 4 all the time because that's what tables have. But in this case here, since this is a 1 decimal place value, you could go more than 1. But you shouldn't go less than 1, because that's too much rounding. So you came up with 2.00, so I'm going to say this is approximately equal to 2.0. So we have some consistency here. If I just say 2, then it looks like I've rounded it to the nearest integer, doesn't it? But 2.0, all right? So what is my answer? Going back to here, it's mu is less than 141.3 plus 2.0, 141.3 minus 2.0. So 139.3 is less than mu is less than 143.3. This is our answer. Now, that's a really small confidence interval. That's a good thing. We like small confidence intervals. We don't want huge. Remember, one of the things we've talked about recently, say, why would we want to do this? Well, maybe we want to design the perfect desk to suit the majority of Mesa College students. Maybe we want to design the perfect Mesa College sweatshirt, but we only have the ability to do one size. So wouldn't we want to get a true average? Okay? Now, that is a very small confidence interval for one simple reason. Our n was really large. Now, in reality, and we said this before, a simple example would be, we figured your company next year is going to make $1 million, plus or minus $10 million. That might be correct, but would that be useful information? So $1 million plus $10 million means $11 million. $1 million minus $10 million means you lose $9 million. That's a pretty big range of outcomes, isn't it? That's probably not useful. $1 million plus or minus 100,000 might be more useful. Your error should be really small compared to the number you're using as your mean, right? You don't want your error to be larger. Again, I can say with certainty the average height of a Mesa College student is between 0 and 1,000 centimeters. I can say that with certainty. But it's not very useful, because 1,000 centimeters, well, that's over 31 feet. So that's probably, yeah, it's true, but it's not really helpful. I would like a confidence interval to be small. Last day when we were talking about probabilities, that'd be like saying, well, we did an opinion poll, and it looks like between 10 and 90% of the people are going to vote for this candidate. That might be true, between 10 and 90%. Is that useful? Couldn't you say that pretty much about anything? From almost nobody to almost everybody and somewhere in between. Well, we'd really like things to be smaller because they're more useful. So, big picture. I have a normal population, normally distributed population, and I know sigma. If I have these conditions, then I can use the z. And what I mean by using the z, I can use up the predetermined z-values that we already know. We're not doing a z calculation, we're using a value we already know, okay? So let's do a similar example. Okay, let's do IQs, all right? We know that IQ, right, we know the mean of the population is 100 and the standard deviation of the population is 15. Does that mean the mean of the Mesa College population is 100? No. We may be way above that, we may be way below, we may be right on. But because the population mean is something, that doesn't mean that applies to every group that you choose. That doesn't mean it applies to every sample. For example, we know the average height of a human being. So of course that applies to NBA, right? Or would you say the average height of an NBA player might be a little higher than the average height of a human being? By like, you know, a lot. Agreed? So you don't say the average height of a human being must apply to all NBA players. No, that's a much taller group. Okay? We have the on-campus Hobbit Club. You know, it probably doesn't apply to them either. Right? They're probably a little smaller than. So I may know this information, but the only part of this I can use for the Mesa College student is this, because I'm going to measure our average, but I'm going to use this because I already know this. Okay? So we collect a sample of size, let's say n equals 48 from Mesa students. By the way, we don't always say it this way because it gets redundant after a while, but what are we assuming about the sample?
They're randomly selected?
It's always random. Because if it's not random, then it's biased, and then it doesn't really matter what results are. I'm going to make sure that I select the smartest people on campus, find their average IQ, and then report that as Mesa College IQ. Would that work? That'd be like saying find the tallest people on campus and report that as the average height. No, that doesn't work at all. No, it has to be randomly selected. We kind of stop saying it every time because that's implied. It's just really bad statistics if it's not random. Again, that's kind of like saying, I'm going to ask everybody here who they're going to vote for president. Now I'm going to start a sample, and I'm only going to ask those people who vote for the person I want them to vote for. And my sample said 100% of the people are voting for this. Well, no. I might as well just make up the numbers at that point. No, that's not random. I'm deciding the outcome before I do it. So we go out and collect n equals 48, and let's say with an x bar of 104.9. So here's what we want to do. We want to find a confidence interval of the true IQ of Mesa College students, okay? So this time let's do a 99%. Actually, the word we usually use is construct. So let's construct a 99% confidence interval, call it a CI, for the true mu of Mesa students. So the implication is I conducted a random sample, so this sample is absolutely representative of the Mesa population. It doesn't mean Mesa's mean is exactly that, but it means that Mesa's mean really should be close to that because it was a good sample, okay? Well, I have my sigma, I have my n. For a 99% confidence interval, that means, what am I excluding?
0.05 on each side.
0.005, one more zero.
0.005.
Yeah, that'll actually change it slightly. So what is the z that corresponds with 0.005? That's 2.576. Again, that's a computer-generated value. You don't need to, I know those because I use those. So that's 2.5 standard deviations away. So we're really capturing almost everybody in this case. So how do I calculate my error? Error is the magic z times sigma over the square root of n. Okay? This is my cushion. This is my plus or minus that I'm going to add. Okay? So let's calculate that. Now, because I reported a mean to 1 decimal place, it's reasonable to report this to 1. And it's also okay to go 1 further. Just don't go less. That's the only thing. So what's a good value here?
Okay, 5.6.
About 5.6. Now this presents an interesting situation here. My sample mean, and by the way, for one individual to be above average, okay, that's one thing. But I have a very large sample, and they're pretty far above average, so doesn't that make it look like Mesa College students clearly are above average? There's no question. Well, let's see if that actually is what we get here. So our confidence interval looks like this. The true value is going to be X bar plus, and on the other side, X bar minus. Well, that means the true, with 99% confidence, and again, I'll explain what that means. With 99% confidence, whoa, 110.5, that's a really high average, by the way. For an entire group, that's actually really high. For an individual, it's above average, but for a group, it's really high. What is it on the other side? It's 99.3. Why is that interesting? Because with 99% confidence, the true value or the true IQ of Mesa College students between 99.3 and 110.5. So it clearly looks like we're way above average, except the lower end of our confidence interval is actually slightly below average, isn't it? So can we say with certainty that we're above average if these were the numbers? We said we're probably above average, but we actually might be a little, ooh, we didn't see that coming, did we? Like, wait a minute, that lends for the possibility. Now, what it means to say 99% confidence, here's the simplest way of thinking about it. You collected a sample of size 48 from a large population. Then you collected a different sample of size 48. Then you collected a different, you collected size 48 samples for the next 10 years. I mean, you collected thousands and millions and bazillions of samples of size 48. Every one of them was a different sample. What that simply means is a 99% confidence interval means 99% of those samples you collected will have the true mean within it. Is it possible you went out and collected literally the smartest people on campus? Is that actually a possible sample? Even if it's random, is it still possible? Remember we talked about heights. Is it possible the tallest person on campus found their way into your sample? Yes. So is it possible your sample was really too big? Is it possible you had the lowest IQs on campus in your sample? So your sample was artificially low. Is that possible? Yeah. How often can that happen in a 99% confidence interval? 1% of the time. So a 99% confidence interval means you can technically have a bad sample 1% of the time because it's a confidence interval. It's not 100%. We didn't measure everybody. The only way you can have 100% confidence is literally to measure everybody or be ridiculous with your error. Make your error so big. I am certain that the average IQ of a Mesa College student is between 0 and 300, considering it's not possible to be 200 or 0. I'll give you an interval that contains every possible value and then keeps going. Well, again, that's completely worthless information. I would like to say, you know what, I've got this. But this interval, I really want to show Mesa College students are above average. Can I say that with these numbers? Because the lower end is still a tiny bit below. But I'm certain that Mesa College students are above average. How can I fix this? It's not fudge the numbers. What do you think, Chance?
Smaller error.
Okay, smaller error, but I don't control sigma. I don't control X bar. What do I have total control over?
The confidence interval?
Sample size.
Oh.
Oh, so how could we make a smaller error, all other things being equal?
Bigger.
Up the sample size. And I've said this before. How big a sample do you take in general? As big as you can possibly afford to take. Remember, time and money are always potential issues. If I'm doing IQ, that actually is both time consuming and it might cost because I have to have professionals measuring. So that may not be an easy thing to do. We talk about athletes. Drug testing is one of the most popular subjects to discuss in statistics because it's all based on statistics. We talk about random drug testing and what's the percentage of the population that's on performance-enhancing drugs if you're an athlete or just in general. There's a lot of versions of this. So why don't they just test all athletes? Why do they only do a few athletes? At the Olympics, why don't they test everybody? Why do they only test a few? Does anybody know the answer to that? It's actually simple. Ridiculously expensive to do a drug test. It is really expensive. Really expensive. Oh my goodness. I mean, it might cost thousands of dollars to do one drug test. I used to compete, many years ago, I competed in powerlifting, a long time ago, weight classes and all that. And a good friend of mine competed with me. He was very strong, absurdly strong. And you had to declare your opening lifts before the contest. And his numbers were so ridiculous that they performed a random drug test on him before the contest. Usually you'd think you'd have to do something incredible and then they'd test you. They tested him before the contest because they said there's no way. And he tested clean. And he didn't make weight. So he ended up not competing anyway. It's kind of a funny story. But the thing is, in the Olympics, you do something absurd in terms of, you did something incredible, they might test you. Okay? Why? Because they're saying, this is outside the norm or outside what we expected. 1988 Olympics. Carl Lewis was a heavy favorite in everything. He was one of the greatest athletes who ever lived. He's a little before some of your time. He was a long jumper and a sprinter. He was the best at both for a long time. And in those Olympics, a Canadian named Ben Johnson, who came out of nowhere, broke the world record. And everybody knew he was juicing. And they tested him, got caught juicing. He was disqualified. Lives in infamy to this day. He broke the world record in 100 meters because he was glowing in the dark on steroids. He was so juiced up. And everyone knew that because he had never won a major race coming into the Olympics. And so Carl Lewis won, and technically his time was still a world record. It was kind of a crazy story. But because something absurd happened, they don't test all winners. They test winners when something kind of crazy happens. Like this is not normal. Now, those of you who watch football in the NFL, is performance enhancers an issue?
Sometimes.
It's kind of always been there. Do guys get caught?
Yeah.
Yeah. And what happens when they get caught?
Suspension.
Yeah. Yeah, they get suspended. And they're going, it's okay, it's worth the risk. Well, yeah, you lose some money, you don't get to play. But the point being, in the NFL, do they test every single person? Do you think they test Tom Brady for performance enhancers on a regular basis? Probably not. Because he's not out there running ridiculously fast or lifting really high weights or throwing the ball way farther than everyone else. As great as he is, he's not doing anything otherworldly. He just makes really good decisions and throws a really accurate football. But there might be somebody out there doing crazy stuff. So when it comes to that kind of stuff, when somebody's really outside the norm, then we question it. But if nothing unusual happened, then we just go with it. So anytime we're performing a confidence interval, again, like we said, it's assumed that it's a random sample. It's assumed that we did everything right. And there's still the possibility of a bad sample. And what I mean by a bad sample, we did a 99% confidence interval. What if the true mean of Mesa College was higher than this or was lower than this? Then this is a bad sample. Because that means with 99% confidence, we still missed the mark. It's possible that our sample was bad. We can't know that our sample's bad. So kind of an easy way to conceptualize this. You and everybody you know is going to go out and measure 48 people. And we got to keep the same sample size. Everybody you know is going to measure 48 people, and we're going to get the IQs. And let's make it simple. Let's say before you started at Mesa College, you had to take an IQ test. And they put that on your Mesa College ID. Could you imagine that? Here's your ID number, and then right next to it, your IQ, just for fun. Let's just say so everybody actually has that. So it's not a measurement. You just say, can I see your card? And you write it down. Can I see your card? And you write it down. So everybody you know, you have 200 people going out there collecting random samples of size 48. Well, you know what? In those 200 samples, 2 of them probably won't have the true IQ. In other words, 1% of them. But 198 of those 200 samples, they will have the true. That's what it means to be a confidence interval. Because if everybody's going out and collecting a random sample, if it's truly random, then the smartest person can find their way into your sample. You didn't choose them. It was random. The person with the lowest IQ could find their way into your sample because there's 48 people you randomly selected. Okay, so that's why it can never be 100% because we're not sampling everybody. But if the sample is large enough, we saw this last day with the confidence intervals around P. If the N is large enough, right, that interval is really small, I feel very confident. I feel very confident in my results. Now, 99% is kind of extreme. Usually, I said, things like pharmaceuticals and cancer research, things that are really life and death, we're more likely to do 99%. Otherwise, it's not life and death that I have the IQ is correct. So having said that, what if we had done a 95% confidence interval? Let me change this. See, this changes things a lot. Let's make this a 95% confidence interval. And what changes in my calculation? What goes here?
1.96.
And what goes here? Approximately what?
4.24.
About 4.2? Does that change anything? Does that change anything? Now this says with 95% confidence, Mesa College students actually are a little bit above average. Oh, so that's one of the dangers. If you make your confidence interval too big, you're going to include, I want to be certain, but if I make it too big, I might include values that really weren't that likely. We shortened it just a little bit. And now all of a sudden, the left end is still a hair above average. Just a hair above average. Isn't that interesting? Now, we're operating under the assumption, again, two things, that the population is normally distributed and we know sigma. Do you think that applies to everything in real life? Knowing sigma is the tricky one. Because I'm going to go out and collect a sample about something that I don't have any background on. It's very unlikely I have any information on the sigma. Or we've just discovered this new Amazon tree frog. We just discovered this last week. And I want to talk about maybe its life expectancy and different things about it. Is it reasonable to assume its population is normally distributed if we just discovered it? No. I mean, there's no reason in the world that we would assume that. So if either one of those things fail, I don't have a normally distributed or I don't know sigma, then we can't use Z. There is another thing we're going to use. Okay. I'm giving you out a new set of tables. I'm going to show you how to use these. We use these in pretty much the same way we use the Z. They're just not exactly the same numbers. Okay, these are called the T tables. Now, they're a little bit different. It's real similar, but they're not exactly the same number. They're computer generated also. A T table is computer generated when I have to use S instead of sigma. I don't have sigma. So I have to use the actual sample standard deviation. And if that's the case, I can't use Z. Not if I'm using S in this case for the tables. So there's some information out here and some language that's a little bit different. So I'm going to give you a really simple scenario. Okay? Let's suppose I think there's 20 of you here. I've scanned about 20 sheets. I know I just had everybody write down their income from last year, and we just found a group average. Based on that group average, do I know your income? Do I know yours? Do I know yours? Do I know yours? No. what if I knew yours? Then do I automatically know yours, Dylan? No. Okay, what if I know everybody in the room's income except Dylan's? I have the group average. I know everybody's income except Dylan's. Do I know Dylan's then? Could I figure it out? I know everybody in the rooms except Dylan's and Chance's. Can I figure both yours out at the same time? No. But if I knew everybody but one, would I know the last one? Yeah, because to know the group average, you know the sum, because you know it was the sum divided by 20. If I knew everybody but one, do I know the last one? Yes, I do. This is the concept of something called degrees of freedom. It's kind of an odd term. What this simply means is, if I have the group average, but I don't have any of the individuals, then I don't have any information. Everybody here could have a different number. But the moment I got all but one of you, then that last one's absolutely set in stone, isn't it? It can't be anything. Now, I have all but two of them. Then yours literally could be anything, couldn't it? So in other words, Dylan made $1 million and you lost $1 million. We'd count that. Everything is fair game. But the moment I know yours, I absolutely know his. So degrees of freedom in this case is always n minus 1. If there were 20 people in the room, then the degrees of freedom are 19. 19 of you are free to be anything, but the moment I know 19 of you, do I automatically know the 20th one? Yes. If I knew anything less than 19 of you, then I don't know. Dylan. So degrees of freedom is always one less than the size of the sample. And that actually has a lot to do with things. Now, in our calculation of sample variance, go back to the calculation of sample variance, our short calculation. It's the sum of the squared scores. I'll write it this way. Minus n times x bar squared over what? N minus 1. But the population variance is the sum of the squared scores minus n times mu squared, which is exactly the same thing, right? The number of people and mean squared, but divided by what?
Just n.
Just n. In a population, you don't use degrees of freedom. You use everything. In a sample, you always use degrees of freedom in the calculations. We didn't know that's why it was an n minus 1. It has to do with bias, and I learned this at the graduate level of statistics. It's actually complicated where the formulas originally come from. But degrees of freedom, now, the larger the size of the sample, the less the n minus 1 really affects things. If I have a sample of size 1,000, 1,000 minus 1 is really not going to change the calculation a whole lot, is it? But if I had a sample of size 5, 5 minus 1, yeah, that might make a huge difference in my calculation. So degrees of freedom is always one less than the sample size. So I want you to look at this table, and you notice on the left-hand side, it starts with degrees of freedom, not sample size. This is already n minus 1, okay? Now, the numbers on the top are the area in one tail. When we did this problem, what did we do? We did the area in one tail, and then we have the magic z. So when it was a 2.5% or 0.025 in the tail, boom. When it was 0.005, we used 2.576, and so on. Well, this t-table, we get really similar numbers. So let's go over, just for fun, find degrees of freedom of 30, okay? Just start with 30. Then I want the t of 0.005, and I want the t of 0.025. Because we know what the z values are. What are the t values? It turns out it's a little more conservative. So with 30 degrees of freedom, the t value that we would use is what? Can you tell me?
2.750.
2.750. And what would it be for 0.025? Area in one tail.
2.042.
2.042. Now, what were we comparing? What was the z value? The z value was 2.576, and over here the z value was 1.96. Are those fairly close? Are those fairly close? Yeah. what you're going to find is that the t-value is always going to be a little bit bigger because it's going to give you a little more cushion. But here's what I want you to notice. That was 30. Now, go down to, I don't know, go down to 1,000. Now go to the bottom of the page. And I want you to notice what is happening to those numbers as your degrees of freedom get bigger and bigger and bigger. This is kind of fun, because this, again, you will never compute this. This is computer generated. So now, degrees of freedom equaling 1,000, my 0.5% t and my 2.5% t. So what's the 0.5% t when it's 1,000?
2.581.
2.581. And here?
1.961.
You're off by 1.962. You're one row off.
Where am I? Okay, yeah.
Now, what do you notice? Wow, that is really close, isn't it? How about this one? Really close. If I keep increasing the sample size, what's happening to the magic t-values? They're getting closer and closer and closer. In calculus, this is called a limit. There's going to be a point where if I keep going, now, I want you to look at the bottom of the t-table. You'll love this. The second to last row says degrees of freedom of 2,000. Would you say that's a large sample? Sample size 2001. What's the next one say? Large. If 2,000 is not large, what's large? Way bigger than 2,000. Like ridiculous sample. Maybe million, I don't know. Assume ridiculously, absurdly large. Now look at the magic t numbers at the bottom of the page. Do those look kind of familiar? 2.576, 2.326, 1.960, 1. Those are exactly the magic numbers of the z-table, aren't they? Those are exactly the same numbers that I gave you for the z-table. Why? Because as the sample size gets bigger and bigger and bigger and bigger and bigger and bigger, the sample's getting closer to the population. Therefore, the accuracy that it doesn't matter if I'm using the t-table if the sample is absurdly large. I'm going to get the same things as I used. That's why in the old days, and when I mean old days, I mean before everybody had access to all the technology that we have today, the rule of thumb was if it was a large sample, remember large being bigger than 30? If it was a large sample, people would say just go ahead and use the z-table because it was too hard to generate these numbers. Because these are computer generated and you didn't have a computer in front of you. But maybe 20, 25 years ago, because of technology advances, we were able to generate these numbers and put them in textbooks. People said, okay, the right way to do it is to use the t-table. When I first started teaching at Mesa College a million years ago, we didn't have t-tables. They didn't even exist. So we had to use z for everything because these were way more complicated to produce. But over the years, now when I went to San Diego State to do statistics several years ago, they said basically you use t-tables almost all the time because normal populations and knowing sigma both at the same time is really rare. To have both of those at the same time is really unusual. But the safety net is, as long as your sample is really large, the value you get with the t and the value you get with the z, as we're seeing, doesn't really change much, does it? So when you're making your confidence intervals, in other words, it's not really going to make a huge difference. It's not that you'll get it wrong, but it's on a close call. You want to get it right. So now let's do a couple of examples where we have to use the t-table. The error formula is exactly the same, by the way. Okay, because what's the error? I've erased it. I'll write it back up. The error formula when I'm using, I have a normal population and I know sigma. Normal, sigma known. Then the error is the magic z, right? Half in the tail, times sigma over root n. Now, it's either not normal or sigma is not known. If either one of these is true, then I cannot use z. Then the error is the t number that we just looked up. So in other words, it serves the same purpose. Times s over square root n. That's still the standard deviation, but it's the sample standard deviation that I measured. If I don't know the population standard deviation, I have to use the sample. That's all I got. So this number here is a more conservative number. I'm going to have a wider confidence interval because this t-value is going to be usually a little bit bigger than this. This number is often a little bit bigger, but if my n is huge, it won't make a huge difference, will it? Okay, so let's do an example of this. All right. I want to construct a 95% confidence interval where n equals, let's say, n equals 61, x bar is 103.8, and S is 19.68. Now, it's a confidence interval for mu. We have confidence intervals for P, and later, next day, we're going to do confidence interval for sigma, but right now it's confidence interval for mu. This is actually very simple because you have all the numbers. You do have to look up one number. You have to look up the t-value you're going to use. You don't get to use the 1.96. Because why? I'm giving you S and not sigma, and I didn't mention normal. So I can't assume normal, and I don't know sigma, so I use a t. So the first thing, identify how many degrees of freedom. I'm going to put D of that. Degrees of freedom is exactly how many. It's a complicated calculation, I know. If you're having to think about it, that means you've tuned out the last 15 minutes of the lecture. What is degrees of freedom? It's a formula. I'll give you a hint. It starts as n minus 1. This is the only thing you cannot miss in your entire lifetime because you're never going to do anything easier. I can guarantee you. I looked ahead. Okay, what is degrees of freedom?
60.
So it's 60. Yeah, the very fact that nobody was willing to, that makes me worried that you somehow didn't listen to anything we've been doing for the last 15 minutes. Yeah, degrees of freedom is n minus 1. If n is 61, then degrees of freedom is 60. That's not a calculation, folks. That's not a calculation, that's given. Now, that tells me where I'm looking on the table now. Now, if I want a 95% confidence interval, and by the way, on the top row it says area in one tail, but it also says area in two tails. So if it's a 95% confidence interval, then how much is in the total tail probability? It would be 5%. Or that's the same as saying 2.5% in one tail, and you notice those are the same column. So 2.5% in one tail or 5% in two tails is the same column, isn't it? So go down that column until you get to the 60 degrees of freedom. And what number do you see? It's a very nice number.
2.00.
Yeah, well, that's kind of convenient, isn't it? The t-value that you're looking at, and it's the t of 0.025, the one tail, or you could say the two tails is 0.5, you got 2.000. Do you notice that the t-values are all computed to 3 decimal places, which is different because in our z-table, all the z's are 2. I find it interesting that they made these 3. And the reason is because in the z-table, we start with the z and we look up probability. So that z-table is already massive, right? I have 10 columns of decimal points. But if we looked up 3 decimal place z-values, do you realize how big your z-tables would be? We'll put it this way, they'd be 10 times bigger because it'd be 10 times as many numbers. So with the z-tables, we're starting with the z and looking up the probability. Here it's just the opposite. We're starting with the probability and looking up the calculated t. That's why they can go 3 decimal places on the t, because we're not starting with the t and then looking up a number. We're starting with this and then looking up the t. So it's kind of, we do this backwards. So I've got this, I've got this, I've got this. This isn't in the calculation. This is so I can look up this. The calculation involves these 3 things here. Okay? So, what is our error exactly? It is 2.000, I know it's redundant to write the zeros, but this is the number I looked up, times what? 19.68 over the square root of
61.
61. The formula is still square root n. I didn't have to do anything to get here other than look up the right t-value. And by the way, what if I totally mess this up and I use the z-value of 1.96? Am I going to be way off if I used 1.96 instead of 2.0? Yeah, it's not going to make a huge difference, is it? It's going to be really close. And you get approximately what?
5.03 or 5.04.
So you get approximately 5.04, and then going back, since my x bars was reported to 1 decimal place, then it makes sense to use 1 decimal place. It is not incorrect to use 2. But again, never go the other way. Always do at least the same number of decimals. It's just safe to say, I'm just going to use the same, not think about it. So now I can say the true population mean is between 103.8 plus 5.0, 103.8 minus 5.0. Huh. That's not a hard calculation, is it? That's pretty nice. So, with 95% confidence, based on my sample, 95% confidence, the true population mean is between 98 and 108. That's not a huge, right? That's not a huge gap. I feel pretty good about that. Okay? So last day we did confidence intervals around the true probability of success. Today we're doing it around the true mu. But what's different is with the p, it's always a population. With here, I might have normal, I might not have normal. I actually have two different things. In the long run, believe it or not, the t-table is actually used far more often when I'm doing analysis. I'm testing a new drug, to see if it's going to work, its efficacy. Should I assume normal distribution and assume I know sigma when it's a brand new drug? I don't have any information. No, so of course I'd have to use t. There's not even a question. You got to use t. I want to test the brakes on the new Lamborghinis. So I got to crash test a few. Do I assume normal? Do I assume? No. So I'm going to use the t with a really small sample probably, just because I don't have any. So if it's a really small sample, it means I'm probably going to get a really big cushion.
So it'd be 98.8.
Did I mess that up? Oh,
Yeah.
thank you, yes. Can't read my own writing. There we go. Fixed it.
My bad.
Beautiful. Okay? So, questions so far? Now, let's do something slightly different. Last day, we looked at how big of a sample do we need? So, let's go back to the IQ situation. All right? We want to measure the MESA IQs like we did before, okay? But the problem was before, we got a really big confidence interval, didn't we? We got one that actually put us slightly below average to one that put us really high. I really like a much narrower range of values. In other words, I'd like to cap the error. Remember last day we said, I don't want the error to be more than 2% or 3%? And then we said, how big a sample do we need? Can we do that in this case? Actually, we can. Okay? So I want to measure MESA IQs, and I know that sigma is 15. I know this. This is not a question. So here's the question is, how big of a sample is needed so that the maximum error is at most, how small do you want the error to be? Give me a number for IQ. 5, 4, 3. You want a small interval. You don't control X bar, that's whatever we measure, but I'd like to know, I'd like to rank. I don't want, hey, the average basic college IQ is somewhere between 80 and 140. Well, Somewhere between extremely below average and extremely above average. That's not a very useful interval, is it? So maybe let's say, what do you want to say, 4?
Yes.
Okay. So how do I do that? Well, let's work backwards. Now, by the way, we have to determine, is it a 95% confidence interval or is it a 99? That's not important yet. So if the error is, now we're going back to the magic z, sigma over root n. And I need to know how big n is. So I've capped this at 4. I know this is probably 1.96. I know that's 15. How do we do this in general? Well, first thing I'm going to do, swap places. So root n is magic z sigma over error, right? Multiply by this and then divide by this. These are swap places. So I now need to square both sides. And that's all I need to do. So n is equal to the square of the magic z, sigma squared, error squared. That's my n. We can do it the hard way and work everything backwards, but it's easier to just do that. Okay, so let's see what that gives us. In this example, let's assume it's a 95% confidence interval, because that's what it's usually going to be unless I'm told otherwise. So how big of a sample do I need? Okay, n is going to equal 1.96 squared times 15 squared over 4 squared. By the way, are we still recording? Can you tell?
I mean, it didn't make like a beeping sound, but the screen is black.
That means it's not recording. That's what
No,
happened
but
last time.
it's always black though. It'll turn off
Let's-
after
let's-
a little bit.
Okay, we're good. We lost the whole lecture last day because it actually it turned off immediately after we started. No, we didn't catch it because we didn't hear it. And the black screen, like you said, often does, but sometimes it's a black screen and then we mess with it, it never comes back. All right, anybody got a number here? Give me an exact value here.
Okay, 54.0225.
Okay, 54.025. Now this is how many people. Now remember we talked about with sample size? Which way do you always round in sample size? Always. Do you remember? It's always up, because if you round down, then your error is going to be a tiny bit more than 4. If you round up, now your error will be a little bit less than 4. So that means I will use, I can say it this way, don't say this number equals 55. That doesn't make any sense. That'd be like saying, okay, your bill is $54, so you got to pay me 55. No, we're going to use 55. That's not that big, is it? So if I had 55 people in my sample, then I've capped the error at 4. Oh, well, that's not too bad, is it? That's pretty good. Now, let's do it for something else now. Let's suppose, okay, we've just discovered maybe a new species, right? That's always kind of a cool thing, or maybe a new bacteria in the petri dish. We don't have any history on it, but we have a lot in our sample. So as long as your sample size is big, it doesn't matter if the population is normal. Now this goes back a few weeks when we talked about the central limit theorem, and I said, from any population, if you take samples of a certain size and you consider every sample of that size, no matter how spread out the population is, remember the sample means got tighter and tighter. The bigger your sample, the tighter your sample means were, until basically if you took really large samples in general, your sample means would look like a narrow normal distribution, which is why if you take large samples, it doesn't even matter if it's normal or not. Think of income. Would you say income is normally distributed or not? Right? Income looks like this. Right? Very skewed. But if I took really large samples and took lots of really large samples, they wouldn't differ by a whole lot. No, Can I get that one sample that has the rich person in it? Sure. But most of my samples won't, so my samples are going to be fairly tight. Now, what if I do have one sample with a really wealthy person in it? As long as my samples were really large, it will have less effect. Oh, well, what do you mean? I grabbed a millionaire, but if you have 1,000 people in your sample, that's not going to make a huge difference. Does that make sense? It's not a million divided by 1,000 is only 1,000. So I might be off 1,000 in my group average. I'm not going to be off by millions. So the idea being, even if you're not normally distributed, if your population, or excuse me, if your sample is really large, you got a lot of flexibility there. You can do a lot. So, big picture. Normal population and I know sigma, easy to come up with confidence interval. It's not normal or I don't know sigma, I can still come up with the confidence interval, I just have to use the t-table in order to do this. That's it. So, this is kind of the way of the world. This is the way we do things. So let's do one more example. Okay? Now I'm going to trick you a little bit. From a normal population, we did n equals 23, x bar is 81.6, and s is 14.37. I want to construct a 99% confidence interval for the, and we always say for the true value of mu. Do I use the z or do I use the t?
E,
How come?
normal population.
Normal population, but
You don't know the sigma.
don't know the sigma. So therefore, z or t?
T.
T. Because I don't know sigma, but it's normal. Now, here is the rule that we use. If it's not normal, by the way, to say it's not normal means we don't know. We would never guess. We don't know. We have to have reason to believe something's normal, or I use the term essentially normal. You know, human heights, duration of pregnancies, SATs. We know these are normal. That's not the question. But I have something that I don't know. You use T to be safe, but here's the problem. I don't know if it's normal or not, so I'll assume it's not, and I don't know sigma. In that situation, your sample has to be at least 30. It has to be at least 30. That's why that 30 was so important. If it turns out, now let's go back to the, I need to crash test the Lamborghinis to determine their, average braking time. Well, it's not going to be normally distributed and I don't know sigma, but I really can't afford a large sample of crash testing Lamborghinis, do I? I might only be able to crash test a few. It turns out if you have that scenario, this is the most extreme, this happens the least often. It's not normal, I don't know sigma, and I have a small sample because I can't afford a big one. There are other methods that have to be used. They're called non-parametric statistical methods. There's a class at San Diego State called non-parametric statistical methods. When I went to State, I took that class, and it was considered the most difficult class at San Diego State in every department at State. That was considered the hardest class at State. And that was the one that stats grads avoided like the plague because it was an elective. I took it because I thought it would be really interesting, and it was really hard. But it's, what do you do in the situation where none of the other stuff works? Really, I can't use the Z, I can't use the T, I have a small sample. This can happen. You have situations where, if you have a rare disease, for example, and you're trying to test medications, but it's a rare disease, you can't have a large sample, can you? Because it's rare. That's the whole point of being a rare disease. I have a rare species of animals and I'm trying to measure things about them. Can't have a large sample because there's not very many of them on planet Earth. You have to have statistical methods to deal with those, and there are special methods. And literally, it's like last class graduate school kind of stuff, so don't worry about it at all. But that is the one area that we don't touch. Not normal, not sigma, and small sample. That's its own separate animal. So if it's not normal and I don't know sigma, I know I have to use the Z table, or the T table, but at that point, the N would have to be at least 30. You notice I did say this was normal. I just don't know sigma. So I can use I said from a normal population, but I don't know sigma. Okay? Does that make sense? So I can use the t-table because it's a small sample, but it's okay. If it wasn't normal, then I can't use a sample quite this small. I gotta up it a little bit. All right, so I wanna make that clear because that is kind of the governing rule that people use in statistics. So when we're testing pharmaceuticals, we know it's not gonna be normally distributed. We know we're not gonna know sigma. So we tended to like to do really big samples because we wanna get it right. So pharmaceuticals might have samples 1,000. Okay? I was just recently contacted, I don't know why, but I get contacted for this kind of stuff fairly regularly. And actually my wife was contacted this time. She has to go in for that wonderful surgery that all of you will look forward to someday, called colonoscopy. It's like, I laugh, I've had a few. It's funny, anything you've ever heard about it, it's way worse. Okay, it's the most horrible thing, but you have to do them because if you get colon cancer, you're going to die. Colon cancer is the easiest cancer to prevent because it is so ridiculously slow. If you get it, it's not curable. If you get it, you're done. So the colonoscopy goes in, detects it, cleans out, and then every few years you got to do it again. But my wife, hers was supposed to be a couple weeks ago, but it got postponed because of things. But she got contacted. You want to be in this experimental study where they're doing certain things, and they need thousands and thousands of people in this study. And what's an interesting thing is I'd never heard of this. The study is, can we detect whether you have it or not without actually having to go into the surgery? There's some new thing. Now, I don't know about you guys, but I would love for none of you to have to go in and do the surgery. It is really, really awful. The only thing worse than the surgery is the preparation for the surgery beforehand. Have you had one?
No, I'm a caretaker for my grandpa, and he's had
We call it the toxic juice that you have to drink for 24 hours. It's stuff that'll make you glow in the dark, but you know, it's the worst thing in the world. I'll just leave it at that. You have to drink it every 15 minutes, and then they say, don't be more than 6 feet from the bathroom. Because you're going to live there for 24 hours, literally. Yeah, it is so awful. But anyway, so this new thing is that there's some kind of screening, I don't know the details, that you can do this screening and it can detect it without the surgery. That's what the experiment is. And they asked my wife to be part of this. I'm like, well, is there a downside? And it doesn't appear. So she's like, yeah, I'm going to go ahead and volunteer for this. They need thousands and thousands of people to do this so that they can look at the overall effect of the evidence and say, will this be effective? Because not only that, it'll save insurance a lot of money because surgeries are really, really expensive and these are, insurance things. Now, having said that, my son, a couple of my kids were asthmatic, the other ones weren't. And when he was young, he'd have issues. And so we would get contacted by people. Would you like your son to be in this experimental study where we're testing this new type of medication and all this? And I'd be like, no. No, basically my son is not going to be a lab rat because that's exactly what they're asking. We're going to try some stuff that could be dangerous. It might not be effective, but because he's been diagnosed as asthmatic, we want to, no, try it on somebody else. If it's effective, then, prescribe it to my son. But don't use my son as the guinea pig to see if it's actually effective or dangerous. By the way, there are people that have to volunteer for these. Oh, no, and they'll give you $20 or something, some token. So do you know who usually ends up being in these types of studies? Often?
Military.
I'm sorry,
I
can't hear.
said military.
No, God, I hope not. No, a lot of times they do this on homeless. And in other words, people who are really hurting, they'll go, well, we'll basically buy them for $20 kind of stuff. I've probably been contacted 50 times over the years asking, do I want to volunteer my kids to be guinea pigs, lab rats for some experimental treatment that, by the way, most of the time I never heard of again. What does that tell you? Yeah. So the point being, they have to do this because they need thousands in their samples because there's no predetermined information. Again, the Amazon tree frog that we just discovered, we don't assume anything, but if I can collect thousands of samples, I can have really, really solid information. So that's what we're doing now. We're saying, how do we construct a confidence interval? The mathematics of this is actually quite simple. I mean, let's face it, there's one calculation. I calculate, well, in this case, I calculate the E. I just add and subtract. That's easy. But it's understanding what are the rules. When do I use T versus when do I use E? That's it. Okay? All right, I'm gonna go ahead and stop here. We got a lot of